Okay, my next story actually is, or most of my story is on this particular paper that came out on revisiting the pillars of creation with this MUSE instrument, which I'm going to tell you a little bit about. This paper has got a long name, gas kinematics of high mass stellar feedback traced by optical spectroscopy, is a part of a project they call Fusion, which is one of the worst acronyms. And they wanted to call it Fusion, but I'm having a hard time finding all those in there. Feedback in massive star forming regions for simulations to observations. So, but some of those letters are in there. But anyway, Fusion is the program that it's working toward. And first, I'll tell you a little about this MUSE instrument, which is the Multi-Unit Spectroscopic Explorer. Here's just and I've talked about this once before, but I have a really nice video I wanted to show you on this instrument. But here is the telescope over here. And here is the instrument, and that's what they call the Nasmyth focus here. And all these banks of things back here are actually the actual light sensors for this instrument. It's a huge instrument. Again, here are those light sensors in the back here. The telescope is off in this direction. I'll show you some real pictures here. It looks nice and neat right here, but here is the real image, the back end of that instrument with all these wires and stuff. And so I got to talk to the PI, or hear the PI speak back in a meeting last June, and he's like, God, I wish we could clean all this up, but there's just like no way they could do that. It just doesn't look pretty, but it all works. So, and here is an image, a panoramic image showing the instrument off over here, and here is the 8.2 meter telescope, about 25 feet across that mirror. And this is just one of the 8.2 meter telescopes at the very large telescope on the mountain of Serra, Paranal. And there's four of them. It's on Unit 4, but I actually don't know which one it's on in this picture. In addition, this telescope is fully equipped with adaptive optics, which is where they fire a laser beam up into the sky, use it as an artificial star so they can correct for the atmospheric turbulence and get better and crisper images from the ground. So I'm going to now show you the video that I had the PI send me on this. And unfortunately, he said he doesn't want to put it on the web. So it will not be, when we post our stories on the website at the end of our for the next month here, I can't show this. So you got one chance to look at it. But just as basically what I want to show you is the complexity of this instrument. I'll kind of tell you, really how capable it is. So it's going to show the light path as you go through this particular instrument. I'll try to point out something. So here they're showing, here's an image of a galaxy. There's the light beam entering here. I'm actually not sure all what this does here. And the amount of optics in here is just incredible in terms of directing all these beams. So now here's the big thing where it's taking the picture, it's laying on to this element right here, and you'll see that all of the images then is cut up into different swaths over here. And so they're going to trace just one of those swaths of light coming in over here. So that is looking at that band on the image there. That instrumentation was my field when I was a graduate student, and I cannot even imagine maintaining something of this complexity. So here now they're going back out to these the optical sensors out here at the end there, and then they are going to be further split up by this mechanism. So here's the swath image. Now it's taking each individual of those and splitting up them into all of these individual images there, and then each of those individual images are then brought through the spectrometer here and split up into their component colors of light. So what this ultimately instrument does is that for every pixel is on the sky in the image, they have a full spectrum of the light from that. Now, despite all those reflections and stuff, and then that data is then goes to the matrix over here, and is then processed to reform that image there. And I'll show you the imagery that I want to have after that. So, but maintaining this, and this instrument saw first light last summer, or maybe a few months before then. We was talking in June there about the first light of this instrument. And so it has tremendous capabilities, as you will see. And so I look forward to all the science that's going to come from this instrument. Okay, so this is in Chile, on a mountain in Chile. Okay, so Kachun showed you this. For those who were here last week, I wanted to show this slide again. This was the image that came out from the Hubble Space Telescope's 25th anniversary last month. It's this Westerlund 2 star-forming complex. It relates to the story that I'm going to tell you that the MUSE instrument did. But it's just a really, really beautiful picture. But here is a star cluster that's formed in this young star-forming region. It's only like a few million years old. This is what we call an H2 region. It's ionized hydrogen, and that kind of sits on the surface of a much cooler, what we call molecular cloud. It's kind of like a blister on that surface there. The hot winds and ionizing radiation from the very massive stars in this cluster, the O and the B stars, are what have evacuated this cavity here, and they're blowing on this gas over here, and they're creating what I want you to draw your attention to are these structures over here, these pillars here, very much like the pillars of creation, which I'm going to show you later. And they are actually formed very similar to like the Garden of the Gods, where the Garden of the Gods, the more dense rock, holds up better to the rain and snow and weather. And even though they're getting blown on by these very, very massive stars. So one thing you didn't see last month is they created a little movie to fly into this region. So they're giving you a little 3D movie here, which is very pretty. But how do you actually create a 3D movie like this? So we're used to going to see 3D movies now in the theater. Those are done by having two vantage points, two different cameras. We don't get that in space. So how do we actually produce this 3D movie? Well, I don't know all the details of this specific one, but the majority of it is kind of faked. You have some good guesses. You do have some scientific data in terms of where things are, but some of it is looking at it and imagining how this thing is actually set up in this structure. So we don't always have all the data that we need to actually reconstruct something in three-dimensional space. So the region I wanted to talk about, and from the observations of the MUSE instrument, is this region M19, M16, what is the Eagle Nebula it's called. And these are what we call the pillars of creation. Same kind of deal. This is in more natural color, so the red is from ionized hydrogen here. And here are the ionizing stars above here that are blowing on these pillars. They're ablating them. So here is the image that was taken by that instrument. It's a composite using all the colors from that big scan, but we'll go into detail of that in just a bit here. And here it is in comparison with the Hubble image of this same space, which is remarkably better there, about a factor of 10 better in resolution, actually maybe a little bit more than that. So you can see a lot more detail there, but this is pretty good from the ground. And so what this instrument does is, like I said, this is a composite image, but that image really in this instrument is a series of many thousands of images, all taken at different wavelengths of of light. So you get a spectrum, which is where we get most of our information on objects, as well as the spatial information that's going on in the picture. So you can get a whole bunch of things. Here's just a few cuts. They're all shown in the same color, but this is an emission line of hydrogen. I think this one was, I want to say oxygen and sulfur, and I can't, maybe it's another sulfur line or oxygen line here. But basically you're looking at different features, the different ionizing gas in this region of space, and you can see they are different, and they tell you a little bit about different dynamics. And I could talk for a long time about all the information that you could get out of this kind of data, but I wanted to get more specifically to what they announced in the story. The press release is one of the informations they get here is this looks like a kind of a blase image here, but here's the outline of where the pillars are, but this is what's called an extinction map. Those pillars sit in, there's still gas and dust around there, and that gas and dust is occulting the light that you're seeing the pillars at. So you can create where is all the dust that surround this pillar, when we call this an extinction map. And so one of the things that we've been able to construct from that, these three regions right here, the one with the highest extinction, which is the highest number here in purple, is this object back over here. And then the green is this one here, and the red is this one here. So this is saying there's less dust in this direction, a little bit more in this way, and a little bit more in that back pillar there. Now the real cool information that they get out of there is velocity information. If an object is coming toward you, the light from that object is blue shifted. If it's moving away from you, it is red shifted. And since we see the spectral features of all the things that are going in there, we can actually see what is the velocity of all these emitting components are in here. So there's a couple things to draw your eye to. You can see the outlines of the pillars there, which are in green. And so objects that are toward the blue are coming toward you. Things that are toward the red are moving away. And you can see that relative to the surrounding gas and dust over here, the pillars are moving toward us, okay, relative to the gas. What's going on there is that this gas is that solar wind that is blowing on these pillars. And so relative to our line of sight, there is some of this gas that it's blowing away from us in relationship to the pillars. So you get all of this dynamic range information of how things are moving, which includes how the cloud is actually evaporating as well. And so a thing that they point out over here that you can see right here, but they blow it up here. At the tip of this, there's this star that's forming, and it's sending out bipolar flows from that, like jets that are going in opposite directions, and you can see that in the data. This side, the gas is moving toward us. This side, the gas is moving away from us. So this is extremely rich data set that they can get lots of information from in studying it. So the big thing that they announced in more of a public press article was the fact that you could use this data, like the extinction and the velocity information, to reconstruct where this object is in three-dimensional space. So I told you about the extinction. There's a higher extinction to this one than this one than this one, meaning that that one is further away, and then use that information as well as other information to basically reconstruct how these pillars are actually set up in space. So I put this one here because, first of all, when they created that image, they actually had to take 9 separate images and mosaic that together to create the entire image of the pillars that I showed you in that first image there. And there's some overlap so that they can get, they can mosaic it together. It's amazing that all the data that they got for their study here took less than an hour to take, because it takes, all of that light in and looks at it. So here's an observer. This is not really to scale, but not only have they figured out where the pillars are in space, but they figured out where they are in relationship to the ionizing stars, which on this scale, this is not drawn to scale, would be further up here in this image. So they showed a couple of images here. Here's just here's the kind of the reconstruction there, and then I will show you they just kind of did a little bit of movie of that grid and how they laid them out. And I realize this is pretty crude 3D, but that's the best that they know that in reality based on their measurements. And then I'll show you the one without all the cutouts. That looked more like the 3D we used to see way back when at least when I was young. And here's a nicer picture of looking at that. Same region. Very short. And then I wanted to show you, but here's back to the Hubble imagery where I'm showing a little bit more of the image. You can see that structure in there. So this is what always amazed me about the first Hubble images that came out. I mean, I can see that this one is out in front. I mean, there's clues like this little finger here goes in front of that one. So your eye, in some sense, is a really good computer. And, we get our 3D vision by walking around. Yes, we have two eyes, and that gives us some depth perception. But a lot of our 3D vision comes by looking at things in context and how we think they should look. And so my guess is a lot of that was going on in terms of that first 3D movie that I showed you of the Westerland cluster and everything. And so this one is, they called that a separate pillar back in here, and that one is further away. And in fact, this one actually is pointing toward you. Now, I have one just last short story, and I just wanted to tell you about just because it was observations. This story actually came out last November, but it was data from this same MUSE instrument. So since I explained the instrument, I thought it'd be cool to show this one. This is actually a combined Hubble image of a galaxy with a very boring name like ESO 137-001. And it's combined of a Hubble image and a Chandra X-ray image, and this is hot gas that you see streaming past this galaxy, and this galaxy is moving in this direction and is falling to the center of a cluster called the Norma cluster. Okay, and so the MUSE instrument in this looked at this particular cluster, and it was very interesting. Before I show that this was not an easy object to look at, ESO always has these really nice images where they actually go into the object, but it was very close to the plane of the Milky Way galaxies. This will demonstrate how small of a spot we actually look at in the sky. But we're looking at a cluster of galaxies is like 200 million light years away, but we're having to look through it through a lot of the stars in our own galaxy. Here, and you can see this continues to zoom up until we finally get to the galaxy right there. So to know that that's there, and then there's a cluster of galaxies in which it's actually falling into. So this is a spiral galaxy, very much like our own Milky Way galaxy. And you can see, and even in that Hubble image there, that you can see this these trailers of material that's coming off. So here is the image from it's in a different, I apologize, in a different orientation there, but here is that galaxy. Here are the streamers of gas that is coming off of that there. And this is answering a very important question is in terms of galaxy evolution. We have spiral galaxies that seem to, in very short time, lose all their gas and dust and turn into what we call elliptical galaxies. What is the mechanism for that happening? We're seeing it right here. This galaxy is moving into this cluster here. The intercluster gas is stripping the material from this galaxy and streaming it behind it. And the next image I will show you is I just thought it was a very interesting. They were looking at a lot of the dynamics of the gas and everything in this collision, and that's what the power of the MUSE instrument is. But one of the things that you can see readily in here, this one is actually color-coded where blue is coming toward you and red is going away from you. Okay, so this gas that's up here is coming toward us a little bit more relative to the gas that's back there. Why is that, you suppose? Well, it turns out that the galaxy is rotating in this direction here. So this galaxy's gas was rotating around the galaxy. It's getting stripped so much that it's still rotating back there. So you're basically looking at almost like a helical streamer of gas that is going around like this as it's being stripped there. Even though the gas here was rotating around because of the center of mass of that galaxy, it still is looking like it's rotating at that point after it's been stripped from the galaxy. Okay, well, that actually ends my portion of the 60 Minutes in Space, and I'm now going to turn it over to Kachun. And I'll be here to answer questions later. Thank you.